Here's a question that looks trivial and traps almost everyone. You've got coins worth 1, 3, and 4, and you need to make 6. Quick! What's the fewest coins? Your brain grabs the biggest coin first, 4. Then you need 2 more, so a 1 and a 1. 3 coins. Feels optimal. It isn't. 3 plus 3 is 6. That's 2 coins. The greedy instinct, take the biggest coin you can, just lost. And that one failure is the doorway to one of the most important families in all of interviewing. The Knapsack family, coin change, its evil twin, coin change 2, bounded and unbounded knapsack, and a dozen problems built on the exact same skeleton. Over the next few minutes, we'll go from that greedy trap to one clean, dynamic programming template that solves all of them. And I'll show you the single, subtlest detail, one swapped loop, that separates people who actually understand this from people who just memorized it. Let's pin down the classic version. Leet code 322, coin change. You're given coin denominations, say 1, 3, and 4, and a target amount. You have an unlimited supply of each coin, and you want the minimum number of coins that adds up exactly to that amount. If it's impossible, you return -1. Unlimited supply is the key phrase. You can use a coin as many times as you like. That makes this what's called an unbounded problem. And hold on to that word, because its opposite defines half of this family. Let's ground it with our example. Coins 1, 3, 4, amount 6. Some options: a 1 used 6 times, or 3 plus 3, or 4 plus 1 plus 1. The best is 3 plus 3, 2 coins. Simple to state, and as we just watched, deceptively easy to get wrong. So why does greedy fail here when it feels so right? Greedy means, at each step, grab the largest coin that still fits. For amount 6, with coins 1, 3, 4, greedy takes the 4, then can only add a 1 and a 1, 3 coins, completely missing that 2 3s is better. But here's the interesting part. Greedy actually does work for some coin systems. The everyday coins, 1, 5, 10, 25, are what's called canonical, specifically designed so that greedy is always optimal, which is exactly why a cashier can make change without thinking. But the moment the denominations are arbitrary, like our 1, 3, 4, that guarantee evaporates. And in an interview, assume the coins are arbitrary. So here's the line. A strong candidate says out loud, greedy is a guess, not a proof. When you can't prove greedy is safe, you reach for dynamic programming, which considers every option instead of gambling on the biggest one. Let's build up, honestly, starting from brute force. And the same question we always ask. What was the last coin? To make amount 6, the last coin I placed was either a 1, a 3, or a 4, and after placing it, I'm left with a smaller amount to solve, 5, 3, or 2. So the minimum coins for 6 is 1, plus the smallest of. Coins for 5, coins for 3, and coins for 2. There's the recurrence. Coins of an amount equals 1 plus the minimum over every coin of coins of the amount minus that coin. The base case, it takes 0 coins to make 0. Translate that straight into recursion, and it's correct, but exactly like climbing stairs, it recomputes the same amounts over and over, branching into an exponential tree. For a real target, like 10,000, it is completely hopeless. Same disease as before, and the same cure. Remember your answers. So we do dynamic programming. Bottom up. Make an array, dp, indexed from 0 up to the amount, where dp of a holds the minimum coins to make the value a. Initialize dp of 0 to 0, and every other entry to a big sentinel. Think of it as infinity, meaning not reachable yet. Now walk A from 1 up to the amount, and for each A, try every coin. If the coin fits, dp of A becomes the smaller of its current value and 1 plus dp of a minus coin. Because we filled all the smaller amounts first, every value we reach back for is already sitting there, solved. When the loop finishes, dp of the amount is the answer, unless it's still infinity, which means impossible, so you return -1. Let's trace coins 1, 3, 4, building to 6. dp fills 1, 2, 1, 2, 2, and finally 2. dp of 6 is 2, our 2 threes. Time is the amount times the number of coins. Space is order of the amount. Clean, and it never gambles. Now, the distinction that unlocks the entire family. In coin change, you can reuse a coin as many times as you want. That's unbounded. But a huge class of problems says the exact opposite. Each item can be used at most once. That's the classic 0-1 knapsack. You either take an item or you don't, and once it's used, it's gone. And here's the beautiful part. The code difference is almost invisible. It comes down to the direction you sweep your inner loop. For the unbounded case, you iterate the amount from low to high, so a coin you just used is immediately available to use again. For the bounded 0-1 case, you iterate the amount from high to low, so each item can only contribute once. Same table, same recurrence, opposite loop direction. If you can explain why that one direction flips reuse on and off, you've proven to an interviewer that you understand Knapsack, not just that you memorized coin change. Now, meet the evil twin. Coin change 2, leet code 518. Same coins, same amount. But instead of the minimum number of coins, you count how many distinct combinations add up to the amount. Coins 1, 3, 4, making 6. You could do 3 plus 3, or 4 plus 1 plus 1, or 6 ones. Count all of them. The recurrence changes shape. Instead of taking a minimum, we accumulate a sum. dp of a plus equals dp of a minus coin for each coin, starting from dp of 0 equals 1. Because there is exactly one way to make 0. Use no coins at all. It looks like a tiny edit from the minimum version. It is not, because now a dangerous subtlety appears, one that trips up even strong candidates. And it hides entirely inside the order of 2 loops. Here is that subtlety, the single most important detail in this whole video. In coin change 2, we want combinations. 3 plus 3 is the same as 3 plus 3, and 1 plus 4 is the same as 4 plus 1. Order does not matter. To count combinations, you loop over the coins on the outside and the amounts on the inside. That way, each coin is considered once, in a fixed order, and you never count the same set, rearranged. But flip the loops, amounts on the outside, coins on the inside, and suddenly you're counting permutations. 1 then 4, and 4 then 1 become 2 different answers. That flipped version isn't wrong. It's the correct answer to a different problem. Combination? Sum 4, which despite its name, counts ordered permutations. Same 3 lines of code, 2 loops swapped, 2 completely different problems. Coins outside for combinations, amount outside for permutations. Say that one sentence in an interview and watch the interviewer's eyebrows go up. Let's zoom out and see the family tree, because every one of these is Knapsack wearing a costume. The mother problem is 0-1 Knapsack. You have items, each with a weight and a value, and a bag that holds a fixed capacity. Maximize the value you carry using each item at most once. Picture a 2-dimensional table. The rows are items, the columns are capacities from 0 up to the maximum. For each cell, You make exactly one decision. Skip this item and copy the answer from the row above, or take it and add its value to the best solution for the leftover capacity. Then keep the better of those two. That take it or skip it choice is the very same move as house robber, just generalized. Coin change is this table with reuse turned on and value replaced by a count or a minimum. Once you can see that two-dimensional take or skip grid, coin change, subset sum, partition, and target sum all collapse into a single idea. Let's write the minimum coins solution and dry run it, because a trace is how you prove it to an interviewer. Here's the code. Make dp of size, amount +1, fill it with a big sentinel, and set dp of 0 to 0. Loop A from 1 to the amount. Inside, loop over each coin. If the coin is less than or equal to A, set dap of A to the minimum of dp of A and 1 plus dp of A minus coin. At the end, return dp of amount if it isn't the sentinel, otherwise -1. Now the dry run, coins 1, 3, 4, amount 6. dp of 1 is 1. dp of 2 is 2. dp of 3 is 1, a single 3. dp of 4 is 1, a single 4. dp of 5 is 2, a 4 plus a 1. And dp of 6 takes the minimum of 1 plus dp of 5, 1 plus dp of 3, and 1 plus dp of 2, which comes out to 2. Answer, 2 coins. Always walk this table out loud. It proves your recurrence and catches the sentinel bug. Interviewers love one follow-up here. Great, it's 2 coins, but which coins? Getting the count is not the same as getting the actual answer, and a senior candidate anticipates this. The trick is to remember your decisions. Alongside dp, keep a second array. Call it from, and whenever dp of A improves using some coin, record that coin in from of A. When you're done, you start at the amount and walk backwards. Look up the coin you used to get there, subtract it, and repeat until you reach 0, collecting coins as you go. For amount 6, that gives you a 3, then another 3. The actual solution, not just the number 2. This store a parent pointer, then backtrack pattern shows up all over dynamic programming, from edit distance to shortest paths, so it's a clean, reusable move worth keeping in your back pocket. Let's collect the traps, because this family is a minefield. 1. The impossible case. If dp of the amount is still your sentinel at the end, the amount cannot be made. Return -1, and don't let a stray infinity +1 overflow your integer. That's exactly why the sentinel is a big number, not the literal maximum value. 2. Amount 0. The answer is 0 coins, and there's one way to make it. Get that base case wrong, and everything downstream breaks. 3. The big one, combinations versus permutations. If your coin change 2 answer comes out way too large, you almost certainly swapped the loops and counted orderings. 4. Never assume greedy, we already watched it fail. And 5. Always know your dimension. If items can't be reused, it's 0, 1, so sweep the amount downward. If they can be reused, it's unbounded, so sweep upward. Name which one you're in before you write the loop, every single time. Here's your payoff. The ladder of problems this one key unlocks. Perfect squares. The minimum count of square numbers that sum to n. That's just coin change, where your coins are 1, 4, 9, 16, and so on. Combination. Sum. List every combination that hits a target. Same skeleton, but you record the actual sets. Combination sum 4. Count ordered permutations. And remember, that's the amount on the outside loop. Partition equals subset. Sum. Can you split an array into 2 equal halves? That's a 0-1 knapsack, asking whether you can hit exactly half the total. Target sum and plain 0-1 knapsack itself Round out the set. Every single one is the same recipe. Define what DP of a means, write the take or skip recurrence, pick unbounded or bounded, and choose your loop order. Learn coin change to the bone, and you haven't learned one problem. You've learned a quarter of the entire dynamic programming section. Let's bring it home. Coin change asks for the fewest coins to hit an amount, and greedy fails because the coins are arbitrary. So DP of A equals 1 plus the minimum over the coins of DP of A minus coin. Never gamble, consider every option. Its twin, coin change 2, counts combinations by summing instead of minimizing. And the loop order decides everything. Coins on the outside for combinations, amount on the outside for permutations. Reuse allowed means unbounded, so you sweep upward. Used once means 0-1 knapsack, so you sweep downward. And store a parent pointer if you need the actual coins back. Master this one template. Define the state, write take or skip, pick bounded or unbounded, order your loops. And the whole knapsack family falls at once. If you want to practice these live with an interviewer that pushes back with real follow-ups, come do it free at crackit.io.